Hey, this is Tony from Adafruit, and in this video I'm going to look at a fun project I just put together that I call the Digital Fidget Spinner. So if you haven't seen, fidget spinners are fun little kind of stress toys that you can use to spin around in your hand. I actually don't have one to show, but I've got a digital version of it here. So this is using Circuit Playground, and the cool thing is if I flick this from one side or if I touch it like that, you can see that it starts moving, and if I touch it from another side, it starts moving faster in a different direction like that. So it's kind of cool. It's a fidget spinner with no moving parts, and the neat thing is because it's digital, I can change its behavior. Like I can change the animation. So if I do like this, it has a nice little sine wave. I can have like a double sine wave like that. Ooh, that's kind of cool. Or I can even change the colors of these. So I can go through like a gradient of colors like that. And then if I flick it from one of the sides here, you can see that it just starts spinning around and it slows down. It kind of has this natural kind of friction-like decay of speed. So we'll look at how to load this. It's an example sketch in the Circuit Playground library. And then I'll walk through the code and kind of show how I created this and how I use the accelerometer, which is a little chip in the middle of Circuit Playground that can detect motion. And notice how, if I move my hand around, it's not detecting that as a spin. I can shake this board a lot, but it's only when I really flick it with a very kind of noticeable, very sharp kind of impulse that it detects that and starts spinning. So I'll show you how I did that. Peak detection is kind of what it's called, and some interesting algorithms you can use to do that because it's a little bit of a difficult problem. We'll look at the data from the accelerometer and see how you can get this noisy stream of data to detect something like an impulse like that, like a flick. So we'll kind of dive in and have some fun here with this project. And then I should also mention this also works. So I'm using the Circuit Playground Classic board, which is the older version of Circuit Playground. It's using the ATmega32U4 Arduino compatible board, but there's also the Circuit Playground Express, and this is a prototype board, so that's why it's a purple color. Brand new, just came out last week. And this also works on Circuit Playground Express, so I'll show both versions of this. Actually, if I plug this in, I will show it right now. So I just have to plug a battery in. And this board has a fancier microprocessor. So this has the Atmel SAMD21. It can run CircuitPython. All of this example code that I'm looking at in this video is all in Arduino and C and C++ based. But I think maybe next week I'm going to do a video to see if I can convert this fidget spinner code into CircuitPython code so that it runs as Python code. There'll be some challenges because it needs to run pretty quickly, and we'll see as I dig into the kind of the code what happens here. But you can see it's running on this board, so if I press, if I hit the side of it, then it starts spinning around. I can press the buttons to change the colors, change the types of animations and things here. I don't know if I showed before, there's a single light mode like that, so you can press that. And then there's also a double, oops, I changed the color, it's kind of a neat color combo. There's a double light mode like that, so you get two little dots that spin around here for these different modes. So again, really neat little toy, and you can see it's a pretty resilient. I can move this around and it's not randomly activating. I can press it from the back here and it's not activating, but if I press it from that side there, then it starts to spin around. So kind of cool behavior. Okay, so let's dive in here and look at maybe the main view, and I'll show you how to load this, like I said first, just if you want to play with this and you don't care how it works, and then I'll walk through the code to explain a little bit about what this peak detection is and why it's interesting and how you might be able to use it yourself to do some interesting accelerometer projects. So we'll go to the main view here, and hopefully the microphone and everything is working. I know last time I tried to do a stream I had some fun problems, but I think that's all sorted out. But let me know in the chat if the audio is a little bit weird. And then also too, I was away for a couple weeks, so I was at PyCon, the Python programming language convention last week, and I was getting ready for it the week before. So we'll hopefully be back to kind of the regularly scheduled Watch Tony D's Desk in the weeks going forward. Anyways, this is the example sketch, but before I get into that, maybe I'll just bring up this web page. So first of all, what is a fidget spinner? Well, it's a little, I think it's a stress toy. I don't know exactly how these are created, but usually you have a bearing, and then attached to that bearing is something you can spin around, and so it'll spin really freely, and you can see in this video. And I don't have a physical fidget spinner, a real one, but hey, I've got a bunch of digital ones now, so that's why I wanted to create this project. I thought of this while at PyCon last week, and it would be a neat little hack, and so I figured I'd put it together, and then it actually turned out a little more interesting than I thought. So and I'll put a link to all the web pages and all the code that I look at in the description below so you can follow along. When this goes up on YouTube, look in the description and you'll find links to all of these pages. So this is just an overview. You can 3D print some cool fidget spinners that Noe and Pedro have created, and I think this is one of many fidget spinners that they've done. It's kind of taking the web by storm. But hey, who can say that their fidget spinner has no moving parts? This one has no moving parts. It's all digital, so that's kind of cool. And then, of course, this uses, like I mentioned, the Circuit Playground board, either the classic board, that's the one that we've had in the shop for about a year, and then the brand new Circuit Playground Express board that just came out last week has a fancier microprocessor, but all of the same peripherals pretty much. So you can have like the little 10 RGB NeoPixel LEDs and the accelerometer in the middle. Those are the important parts and the things that we use in this example here. Now, to use this code to just run the sketch, you need to get the latest version of the Adafruit Circuit Playground library. If you use the library manager in Arduino after like tomorrow, then it should be updated. But if you haven't gotten it yet, I'll put a link in the description. You'll want to go to the GitHub repository and download the latest version here because I just added this to the library. It's version 1.6.5 of the library. If you look at the releases here, that's the release that adds the digital fidget spinner example. And just in Arduino, look in the examples. If you don't see fidget spinner, you might need to go into the library manager and click the update button. And I'll show you real quickly too inside of here. So if you do manage libraries, and then if you search for circuit, and then it should show up Circuit Playground, make sure that you have version 1.6.5. You'll see something weird for me because I've installed this library manually, so it's not using the one that's in the library manager. But grab the latest version, and if you don't see that 1.6.5 version here, then you'll have to go to this GitHub repository and install it the old-fashioned way, which I'll put a link in here, Arduino library install. We have a little guide that shows you how to install an Arduino library, so go to this guide and it will show you what you need to do to manually install a library. Okay, so once you have the library installed, then you should see under the examples for, come on, open this up. Under examples for the Circuit Playground library, the fidget spinner example. And so that's what I have open right here. And so this has all of the code for this project. And if you just want to use it, so you'll need a board like Circuit Playground. I'll take a classic board, for example, and I'll plug it into my computer. And you can see in the upper right corner, this is just a battery right here, so we'll use this in a second. If I unplug it, then I can power it off the battery. Okay, so I will select the board, so make sure that you have Circuit Playground set up and that you're able to load examples and things on it. I've got Circuit Playground selected right here, and here's the port for the board. And by default, you don't need to really change anything. If you're using Circuit Playground Classic, you're good to go. If you're using the Express board, take a look at the accelerometer in the very middle. It's this tiny little chip. Yeah, you can see in the very, very middle. Oh boy, my fingers here. So right in front of my fingernail, you see that XYZ? That's the accelerometer. And so you want to check which axis of the accelerometer is going to be the one that's determining how you flick it. So you have to kind of figure out which axis you want. So there's, on this board, the y-axis goes up and down when I hold it in this orientation. So that means if I flick it from this direction, that's a negative flick, and then if I flick it from this direction, that's positive, so that's a positive flick. It's going to detect that as a positive force. So let me refocus this camera here. There we go. And then on this board, it shows the x-axis is going this direction, and the arrow is pointing this way, so a flick in this direction is a positive flick, and in this direction is a negative flick, because it's the exact opposite side. And then the z-axis on both these boards is the same. It actually goes into and out of the board. It's a little bit weird. It'd be like if I tap the board from here, that would flick it one way, and if I tap it from the back, that would flick it another way. But you can change which axis you want to use. So look at your board and see, by default, the sketch is configured for the y-axis. So on your Circuit Playground Classic, the y-axis, when your micro USB connector is facing down, your y-axis positive direction is this way, like to the left here. So if I flick it that way, that's a positive flick, and that way it's a negative flick. But if I want to change it, I could say, let's use the x-axis instead. So I just uncomment this line and then comment the other line. So only one of these axis defines should be uncommented. So for example, if I wanted to use the x-axis, this would work well for Circuit Playground Express in this orientation. So with the micro USB facing down, then it shows the x-axis positive is this way, so that's a positive flick, and that's a negative flick in this direction for it. So just a few little options you can tweak here, and you don't have to use those axes. You can use, if I wanted to use the y-axis on this board, then a flick this way and a flick from the bottom there would change kind of how it spins, how the motion moves. The other option here is you can invert the axis. This just means, in this case, if the x-axis, the arrow is pointing this way, so that's positive x. So when I flick it this way, then it's going to assume that the pixels should move in this direction. But if I flip that invert axis to true, then it's going to move the pixels in the opposite direction. So this just helps if, in some cases, the movement of the pixels is opposite the movement, the direction of the axis. So if you flick it from a side and the pixels spin in the opposite direction that you expect, turn this invert axis on. And I noticed for Circuit Playground Express, just the way the NeoPixels are oriented versus the way the accelerometer is oriented, you want to have it with that y-axis and the invert axis true. So the default settings for this, and it's all good for Circuit Playground Classic. For the Express board, again, you'll want to probably change to the x-axis, but it doesn't hurt to play with the y-axis also. There are a few other things you can change: the brightness of the pixels. This board over here is full 255 brightness, whereas the Classic board, the Express board I was showing earlier, is a little bit less bright. So you can scale this up and down, any value from 0 to 255, where 255 is maximum brightness. If you use 0, it's going to be turned completely off, so you probably don't want to use that value. So if it's super bright, set it down to a value like 10 or 20 or 15, 50, something like that. I'll just play around with it and see. We'll come back to what these values are here. These control the peak detection, and we'll play with these in a moment. And then there's some button debouncing logic here, which you don't really need to change. If you do want to change the colors, though, it's down here in this color combos. So I made this kind of complicated struct thing, and hopefully when I do a CircuitPython version of this, we'll be able to show why Python code is maybe much more interesting in some cases, or much more fluid and expressive compared to Arduino, because this little block of code is just making a list of color combinations, but you can see all this crazy syntax. You have to make a struct and then this initializer list syntax in C and C++. It's cool that you can do this, but in Python this would be like half the code and much more expressive and make a little more sense. But if you want to add or remove colors, just add or remove lines right here, and you can see each color is defined. There's a combination of a primary and a secondary color. So the very first color, it starts out with red as the primary and black, or 000, as the secondary color. These are 24-bit RGB color values. Just think web hex colors. So like FF0000, that's full red, no green, and then no blue intensity for this. So you can see some examples here, and you can add more colors up to as many as fit into memory, which would be quite a few colors in here, but each color has to have a primary and a secondary color. And be very careful of the commas. If you add and remove lines, every line has to end with a comma except for the last one, and you'll get a nice little error from the compiler if you don't get that right. So just be aware of that. And that's all that you need to change. There's just some state here that's kind of global, and I'll walk through more of that. And then all of the main sketch code, there's just a little bit of setup and some loop functions here. Okay, so once it's all ready to go, I have my board selected. I'm just going to press upload, and this should upload to the board in a moment here. It's going to compile it, and then it's going to push it out to the board. So it's writing the flash memory, and it just pushed to the board. So now it's running. And so if I look at it, let's see, or here, maybe I'll hold it down here so you can kind of see. So if I just tilt it a little bit so that I can kind of flick it from a certain side. So if I flick it this way, you can see it starts spinning like that. And then if I hold it here, and if I flick it from this way, it's a little bit harder for me to flick my finger. There we go. If I flick it that way, then it spins the opposite direction. And you see, sometimes it gets it wrong and it actually spins the opposite direction. That's kind of normal, and we'll see why in a moment that's happening. But that's all you need to do. And then there are a few buttons you can do. So if you press one of the buttons, that changes the color. So that's just cycling through all of these color values here. So it's red, green, The next one should be blue, and then you can see it does some color combos here where it's green with a red dot, blue with a red dot, and then blue with a yellow or with a green dot. And then the other button, this changes the type of animation. So it starts out in single dot mode, but there's a double dot mode, which I think this is kind of cool because this just shows more of the kind of spinning nature of it. So it gives you a nice kind of effect like that, and it looks like a bar of colors that's spinning around. Another option is this is a single sine wave, so you can see it's like a nice little gradient from blue to green. And then when I flick it, let me see if I get a really good flick inside of here. There we go. Trying to get a fast one. It's a little bit hard to get a fast flick. And I also have a delay where after you flick it, it waits 500 milliseconds for you to flick it again, because you'll see there's some debouncing logic that you kind of need to do to this flicking. But you can see it's moving that pulse around. And then if I press the button one more time, so there are 4 animation modes. This is in a double sine wave mode, so you can see there's like 2 of those green pulses. So that one, I can flick it, and it's kind of cool. It makes a nice little smoothly animating kind of pulse like that. So really cool little thing. And like I said, it's the only fidget spinner that has no moving parts that I'm aware of. Maybe this is the first digital fidget spinner. I'm sure it won't be the last digital fidget spinner though. So because all this code is open source, so hey, you're free to take it and go crazy with it. Okay, so let's play a little bit with the code, and maybe to start with that, I'm going to open a different example because maybe first I'll show you if you load the Mega Demo example in the Circuit Playground library. So Mega Demo, load this example and put it on your board. I've already got it on this board. Mega Demo has a good way to visualize the accelerometer values. So when you start it out, it starts with just this NeoPixel animation. You can press one of the buttons, like this right button here, to change the mode. Now it's in a sound sensing mode. The next mode is Capacitive Touch. So if I press some of the outside pins, it detects them when I'm grounded. If I ground myself there, so you can see it kind of detects some of those presses. And then if I press it again, now it's in a mode, this is the accelerometer mode. And you won't really notice much, but if I move the board around, so notice this, when I have the board in this orientation, the pixels are red. But if I flip the board around completely and then show it to you this way, now it's blue. And so if I change between those orientations, it's going to smoothly change the colors like that. And that's because it's using the accelerometer, that chip in the middle, to detect the force of gravity. So the accelerometer is basically just detecting constant acceleration. So that's basically able to tell me that, okay, hey, there's some force pushing down on this thing. And then I can, by looking at a certain axis, because there are 3 axes, like I said, on this board, there's a z-axis that goes up and down, x-axis goes this way, and y-axis goes this way. I can look at all 3 of those axes to kind of figure out how this board is oriented relative to gravity facing down. Now in this mode, if I press the other button, this changes which axis it looks at. So in this mode, I believe, yeah, if I tilt it this way, so now if I tilt the board this way, it turns red, and if I tilt it this way, it turns blue, like that. So it's just changing the axis. In this case, it's using the x-axis, so just how I tilt it changes the colors here. But the cool thing is, if it's looking at the x-axis, if I flick this, it should change colors because I'm going to apply a force to this board. It's not the force of gravity, but it's a force for sure when I do this. So notice, do you see it flash blue for a second there? So it might be a little hard to pick up because it happens so quickly. But you can, when I'm looking at this, I can kind of tell with my eyes. It's pink and then it turns blue really quickly. And so what's happening there is when my finger touches the board, it's imparting some force on the board that's moving the accelerometer, and it's detecting that as a spike or a change in the acceleration. So that's basically what my fidget spinner does, is it just looks at one of the axes and just looks to see, do I see a positive spike or a negative spike? And then when it detects that, then it just goes into an animation. And so the animation is just, given a starting velocity, I can just figure out, okay, how fast should these pixels be animating? And I can apply a little bit of a slowdown thing to it. But all of the magic of detecting, when this thing is actually being flicked is coming from that accelerometer. So it kind of helps to use that Mega Demo example as a way to just kind of visualize, you can move the board around and start to intuitively understand, what it means for the accelerometer to be facing in different directions, and even just like tapping it, you know, kind of what happens here. But something else that's interesting, I can actually graph the values of the accelerometer. So we can look at, you know, what do I see on that x-axis or that y-axis when I'm tapping the board. So let's do that. Let's open up an example here. Let's go to the Circuit Playground library, and let's go to Hello Circuit Playground, Hello Accelerometer. Let's look at this example. So this is a really simple example that shows how to use the accelerometer on the board. And basically it will just open the serial port at 9600 baud, and it will get the x, the y, and the z axis accelerometer values, and then it will just print them out. And so it's going to print out x, y, z values like this. So if I save this, and I'm going to upload it to this board right here, and then let's see, let me press the upload button, and we will open up the serial monitor, and we'll take a look at what the values are for this. So it's uploading, and then now let's open up the serial monitor, and I need to do this at 9600 baud, so I'm going to close it real quick. But you can see every second it's printing out the accelerometer values, and so this is kind of cool. You can see one of the axes is showing 9.6, that's the z-axis, and that's actually good because that's the z-axis is the one that's going down like this. So it's showing me that there's a 9.6 meters per second squared force applied to this board, which as long as I'm still aware, I'm on the planet Earth, that's what we expect. 9.8 meters per second squared is the force of gravity. It's a constant force down. Cool thing is, if I flip it over, then notice that z-axis value inverts. So it's negative 9.8 roughly. And that's because now the positive axis is facing the opposite way. Gravity's still going down as far as I know. I haven't flipped gravity over completely yet. So it's just, I see it as a negative force. And if I hold it kind of halfway like this, then you see like you basically get a zero value. Like there's no force of gravity being applied to that axis as far as it's concerned. But now look at the y-axis in the middle. That one's showing a 9.8 roughly meters per second squared force. So that's another cool way to kind of interpret the accelerometer values. Now let's see what happens if I flick, let's see, the y-axis, the way I'm holding this, the y-axis positive is going this way. So I'm going to flick it in this direction and look at the y-axis values here. Now, the flick, it's only reading this once a second, so I might not pick it up. So I'm just going to have to flick it a bunch of times, and we'll just see if I can kind of pick one up. Looks like, all right, we're not picking it up there. So let's increase how quickly it reads these accelerometer values. So you can see it delays for a second. Let's delay for 10 milliseconds. So this is going to do 100 times a second kind of sampling here. Oops, I don't need to save this thing. And then, okay, so let's upload this to the board again. This is going to go very fast, but we should hopefully be able to see like a spike. And then I'll show you in a second how to use the serial plotter in Arduino to visualize this data. Okay, so this is zooming by, but now, okay, yeah, notice when I flick this thing, you see there's some big set of data goes streaming by. Okay, so let's see how we can visualize that data. So to use the serial plotter in Arduino, you can actually plot any comma-separated values. So this sketch by default is just showing you kind of the XYZ values. If I change it slightly, so if I uncomment these lines that kind of print out, you know, the nice labels that me as a human would want to see, and if I add in a comma between these, so if I put a comma here, and then if I also put a comma after this value, now I should be able to see comma separated values. So let's upload this to the board, and hopefully it's not stuttering. I'm noticing my CPU usage is starting to skyrocket a little bit, and that's probably because the serial monitor is open. So we'll see if I can get this over with a little bit quickly to show the values. Okay, so if I open the serial monitor again, you can see there's all the values, but they're all comma separated. But now, instead of opening the serial monitor, open up the serial plotter and make sure to get the baud rate correct. And so this is really cool. This is a feature that was built into Arduino last year, I want to say, maybe the year before. And it's just a way where, again, if you have comma separated values, it can plot them automatically. So this is showing all three values, and it's just showing them in the order that they're printed. So blue, red, green, so that's basically X, Y, Z axis acceleration. So you can see one of the axes is way up around 9.8, and that's the Z axis, which is what I expect. But then if I move the board around, that's kind of cool. I just tilted it this way. So you can see one of the axes jumped up to that 9.8 value, and the other one kind of went back down to like a 0-ish value. You know, if I can move the board, I can shake the board, and you can see all these crazy values and things changing. But let's try when I flick one of the axes. So I'm going to flick the y-axis, and that's the red line. So let's see what happens to the red line when I flick it. So, okay, check that out. You can see that spike that happened there. And all three of the axes kind of saw a spike, but you know, the red axis in particular saw a pretty big spike. And all of them kind of see a spike because, you know, that flick is going to kind of vibrate through the whole board. So all of the axes are going to see that motion. But it's kind of, okay, so notice that one. That's a really good spike. So the red saw a big spike, and then the other axes kind of saw a more moderate, kind of damped spike right there. So that's my challenge, is I want to detect that red spike and nothing else. You know, I don't want to detect when I'm moving the board around like this. You see all this noise that's happening. Like, there are all these little mini spikes here, but they're not really big spikes compared to when I flick the board. You know, notice how the signal is really stable, and then that flick comes in, and it's a huge change compared to the rest of the values there. So that's kind of the challenge, is how to detect that. And so maybe to make this a little more obvious, let's just graph the y value. So I'm going to comment everything out except for printing the y-axis, and make sure to print line because I want to make sure to end it with a new line so that the serial plotter can pick it up. So this is only going to plot the y-axis acceleration. And so this will just make it more clear, you know, what happens when you flick that axis with your finger. So we'll open the serial plotter again. And now you can see, so that's just the y-axis, and you know, if I move it around, there's some random noise, stuff like that. But then when I flick it, you get that nice big impulse. And if I flick it from the opposite direction, like that way, so you notice it went positive kind of initially. But if you look really closely, it kind of goes up, and then it goes back down a lot, and then it goes back up, and then it goes back down. It kind of rings, so it goes up and down and up and down and up and down. And that's just because the board is kind of shaking. You know, my move, like if I shake my hand back and forth like this, I can make a really nice kind of, plot like that, a ringing plot. Whereas, you know, when I flick it like that, I get a quick little impulse up and down. So that's another challenge here, is that, you know, I want to detect that initial spike, but I don't want to detect when it kind of comes back. I don't want to detect that as another spike. And so I kind of want to debounce that logic, or stop listening for a while to, you know, I just want to capture that initial spike and then go from there. Now, okay, so the big question then is, how do you detect that peak? One simple, the kind of naive approach is you just set a maximum value, like a window that you're looking for peaks. So you can see, like when the board is held like this, you know, all the values are pretty stable, but if I smack it like that, I get this big spike, and so I get a big acceleration down to, like, you know, roughly like -9 or so in one direction. And if I smack it from the other direction like that, you know, I get a big spike up here, up to about +8, or, you know, even -16 down there. So I could just put a threshold in here in my code that just says, if I see an accelerometer value above, like, let's say 5, then consider that a peak. And so that would pick up a case like that, where, you know, I could say if it's above or below 5, like -5, then it would capture that peak and consider it, you know, something that causes a spin. The trouble is, though, what happens when I start moving the board around like this? You know, I pick the board up, or I put the board down like that or something. You know, just that little movement is causing some of these spikes that I don't necessarily want to pick up. Or you know, that threshold value, like if I hold the board in this orientation, you know, I'm getting a mostly 0 value, but now when I rotate the board like this, now I'm getting like a +10 value, and if I set my threshold to 5, I'd be firing constantly. It would constantly think that there's a flick happening to this board, you know, just because that's the force of gravity in this orientation that's causing it to see that force. You know, I can still flick the board, and I can still detect those flicks. It's just now I'm at a constantly higher level because I have that force of gravity applied to it, and I can move it back down. So that's where that kind of window or threshold peak detection kind of falls down, because, you know, if you don't have control over what the kind of steady state values are, or if that steady state value changes, it gets more difficult. You know, you can't necessarily detect that peak with that simple kind of logic like that. That simple approach definitely works though, and it might be kind of the first option to think about, but you might run into trickier cases like this where you need to maybe filter out some of that noise or account for the fact that, you know, there's a steady state and then a big change from that steady state is what I want to look for. So I thought about this, and actually I looked around, and there are a bunch of solutions out there already. There's I think a whole bunch of different types of algorithms. If you search for peak detection, you'll find a lot of algorithms. I just intuitively started thinking about this, and you know, my general thought is, okay, you know, I want to define what is a steady state for the accelerometer value. You know, what is, like, when it's held in this orientation, it's going to settle down to some steady state. If I hold it like this, that steady state might change, you know, just based on the force of gravity. But I want to figure out what is that steady state and be able to update that dynamically as the board moves around. And then I want to find any time an acceleration value comes in that's orders of magnitude different from that steady state, either positive or negative, then I could consider that a peak. And so I was just kind of thinking, well, what if I filtered the values? I just took the average of the last, you know, let's say 10 accelerometer readings. So I average all those out. That's going to give me a less kind of quickly changing value. You know, it's going to give me the average so that if I have some random noise of just moving the board around, it's going to smooth that out so that I don't see all these jaggy spikes. You know, it's going to look at all 10 of the last readings, and if all 10 of those are really jaggy and high, then okay, it's naturally going to push that average value up. But if only one of them was a small spike, that's going to get filtered out, and it's not going to impact that value as much. So that gives me kind of my baseline, and then I could compare my readings to that baseline to see, okay, how far are you from that average value that I've computed? And once you get beyond some threshold, then I might consider that a peak that I've detected. And so that would be good, because that would protect against this case where, you know, I move the board into a new orientation. Now the new steady state is maybe above some threshold value. But that's okay, because I'm not looking at a fixed threshold. I'm looking at just the last 10 readings and what's their average value as my kind of baseline steady state. So as the board changes, that baseline steady state kind of slowly changes with it. And it turns out that that is actually a really well-known, maybe not really well-known, but is a good algorithm that that folks have thought of ahead of time to do that kind of peak detection. So I'm going to close out of that sketch. And I'll show you, I'll put a link to, of course, Stack Overflow, the very first choice of when you are in doubt about something, you search Stack Overflow. And there's a great question here that talks about this exact problem. How do you detect the sudden peak in time series data? And it talks about the chosen answer here is called the smoothed z-score algorithm. And basically this is doing exactly what I just described, where you're smoothing out your values so that you figure out what is your baseline steady state. And then when new values come in, you compare them to that steady state, and you see if they are some number of orders of magnitude above or below that value, then you found a peak effectively. And so what this does is it's actually computing the average of a window of the last seen values. So that's kind of one thing you can tweak here. They call it lag, and so that's how many of the last accelerometer values do you make that window. So, you know, you can have like 5 readings, so the last 5 readings it will average. You go to like 500 readings if you want, so the last 500 readings will average out. And this is where, like, this algorithm is not a one-size-fits-all kind of thing. You're going to have to tweak these values a little bit depending on your application for this. But that's one knob that you have for this algorithm. There's a threshold value. So what this algorithm does is it, for that window of values, let's say it's 5, it will average the last 5 readings to figure out what's the average value. And then we'll also figure out what's the standard deviation, which is kind of a measure of how far do most of the values differ from that average value. It's a statistical method. It's kind of telling you how noisy is your data. You know, when the standard deviation goes up a lot, it means that most of your data points aren't near that mean value. But when your standard deviation falls down to 0, then that basically means that most of your data points are clustered around that average value. So you have a very kind of steady signal. But then when your standard deviation goes up, then you have a very noisy signal potentially, or like a lot of your values might be far away from that average. So this algorithm uses that to compare when new values come in. It can look at, okay, how do you compare that standard deviation? You know, are you multiple standard deviations above or below that average value? And so that's a way to detect, are you an order of magnitude different from that average value that we've been computing there? And that's pretty much all that it does. There's one last knob. It has this thing called influence, because the thing is, you know, when I get those impulses, those big strikes that are, you know, big jump in the magnitude, the value, I'm going to save that as a reading, you know, because it's going to average out the last 5 or 10 or whatever readings. And so that all of those readings include the really big spikes from when it detects an impulse or a flick. But this actually adds a knob here to say, well, maybe I don't want those flicks to count as much in my averaging, because it kind of throws it off. Like, you know, those flicks are an anomaly. It's, you know, it's like something hit the board, and, you know, I'm keeping track of this steady state, and I'm using that to figure out when a new value comes in that's far away from that steady state. I know that that's a flick or some kind of, you know, big impulse against the value, but I don't necessarily want to use that big value in my computation of the average going forward, just because that's going to skew the average. It's going to push the average a lot higher and change that steady state, when in reality that was just a quick little impulse value that I don't really want to care for. This is kind of cool in that it adds this influence parameter that just lets you control how much of the peak values should be mixed back into the average. And so this is the value between 0 and 1. And it kind of shows, okay, there's a default of 0.5, so you only count the peak impulses at half of their value effectively for this. So okay, that's the pseudocode. You don't need to implement this because I've actually gone ahead and implemented it in this sketch here. And so I put this in this tab at the top. If you haven't seen, Arduino can have multiple files. So in this peak detector.h, I created this peak detector class that basically just implements this algorithm exactly from that Stack Overflow question. And so I've given it 2 functions that you can call, well, actually just really one function that matters, this detect function. So you create a peak detector object, you call detect, and you pass it a sample. So you pass it some floating point value, like an accelerometer axis value, and it will return an integer value. It will return 0 if no peak was detected. It will return 1 if a positive peak was detected, and -1 if a negative peak was detected. And that's all that it does. So you just keep calling detect over and over and feeding it new data, and it'll tell you when it detects a peak or when it doesn't detect a peak in this case. And there are a bunch of options that you can change. So when you create this, you can pass in the lag, the threshold, and the influence values, like I was mentioning before. And so that's in the Stack Overflow question, which will be linked in the description when this goes up on YouTube. But again, the lag is basically how big is the window of samples to keep when I'm doing this averaging of samples. So the larger that lag value, the more it smooths out the movement of the accelerometer. So that's one thing you can change. The threshold is the number of standard deviations beyond the mean for an impulse to be considered a peak. So that sounds kind of complex, but basically the higher you set this threshold, the stronger the peak has to be for it to be considered a peak, or the stronger that impulse has to be. So the lower the threshold value, that just means that an impulse that's not as large relative to that average value could be considered a peak. And so again, this is a knob that you might use to tweak your behavior. Like, I want a really strong value here because I want to detect a strong flick, not just a little tap basically on here. And then this influences, again, how much of the peak value should be mixed back into the average. And so this is a value that goes from 0 to 1, where 1 means I want the full intensity of that peak to be mixed back into the average, which maybe you want. It might be worth experimenting with to try and see kind of how that changes behavior. Whereas a smaller value like 0.5, 0.1, that just takes some percentage of that peak value and puts it back into the average for it. So that's all that this class does. I added a few extra functions though. I added a get average and a get standard function to get the average and the standard deviation, because as this thing runs, so in this detect logic, it pretty much follows exactly the Stack Overflow pseudocode for this. I have a concept of, is it primed or not? Primed just means, have I received enough samples to fill my window? So this won't detect any peaks until it's been primed with at least enough samples to fill that lag, that window of the number of samples it needs. because it basically needs that to get a good start to how much data is being fed into it and be able to kind of prime the pump and get that average. So it just checks to see, once it's primed, if the absolute value of your incoming sample minus the current average value. So that's looking at like, what is the distance between your new sample that's come in and whatever that moving average is, that's, you know, your smoothed out filtered data. It looks for this distance right here. And if that's greater than your threshold times your standard deviation. So your standard deviation kind of tells you what is the average distance of most of those values inside that average from each other. And so that threshold just multiplies that out to some larger factor. So if this distance, your threshold times your standard deviation, if that's less than your distance between your sample and your average value, then you've detected a peak effectively. And so that's what this check is doing right here. And then it just looks to see which direction was that peak. You know, is my sample positive or is it negative? And so that's how it figures out which way the direction should go for this. And then it will just save that sample value back in the window of filtered values. This is a circular buffer that I'm keeping here. But you can see here, here's where it does that mixing. So it uses the influence to figure out, you know, only take some percentage of the sample and mix in the previous sample before it if you're kind of combining these two values. And so that's what's happening here. If I did not detect a peak, if that distance between the sample and the average was smaller than that window of your standard deviation times your threshold, then it just saves the value. So it just throws it into your value filtered values. You know, it just says, hey, I got a sample, and we're going to average that out later. And then at the end here, once it's primed up, it will go through every iteration and recompute the average. So it goes through all the values in that window and just sums them up and divides by the number of values, so you get the average. And then once you know the average, it actually goes back through all the values to figure out what's the standard deviation, because the standard deviation is the average distance of your values from the mean. And so again, you know, it needs both those values to figure out these thresholds. So that's everything that's happening inside of this peak detector, is really just some statistics and some math inside of here. So it's not too crazy. It might look a little complex, but it's again just everything implemented in that Stack Overflow kind of answer. And so that's what these values are here in the configuration of the sketch. So this is where you can tweak these values. Now, I've set them to values that kind of felt right for me, just kind of playing with this, but feel free to tweak these values. So lag, I've set to 30. This is how large the window is. So I found I needed a window of about 30 samples. And this might change. So if you sample faster or slower, you might need to increase or decrease this window. You know, the larger this value, the more samples you're going to average together. So it kind of slows down in some ways the behavior. You know, if you're if this is attached to like a car or a motorcycle, you know, something that's like vibrating and like shaking a lot, you know, maybe I want to increase the size of that window because I know I'm just gonna naturally have a lot more noise that I want to filter out. So I want to increase kind of my the length of that window so that I get more values to average out. Whereas if it's just static and sitting on a desk like this, you know, maybe it's not seeing as much force, and a smaller window might be okay. The threshold, I set this to 20, so that means an incoming value needs to be 20 standard deviations beyond the average to be considered a peak. So that's a big difference. I mean, statistically, when something is like 3 or 4 standard deviations beyond the average, then that's kind of a significant change. So 20 is kind of telling me I need a big impulse for this to be triggered as a peak. And then influence is how much of those peaks get mixed back into the average. And I noticed if I set this to a lower value, it seems to behave a little better. But again, you can play with this, any value between 0 and 1 for this. Now there's a cool thing. I think by default, I have the debug mode turned on. So I'm going to load this sketch back onto my board and just make sure I have my axis set up. Yeah, my y-axis set up. So let's upload this to my board again. And I'm going to open the serial plotter, because when that debug mode is turned on, it's actually going to plot a bunch of values that are kind of cool. We'll actually be able to visualize how this peak detector is working. Okay, so it's sent to the board, the code. I'm going to open the serial plotter now, and you'll see some things are being plotted right here. So there are 4 values being plotted. So the blue value, the first value, is my raw y-axis acceleration value. The red value is the peak detector's moving average. So that's for that window of 30 samples, because my lag value is 30. It's what is that average value for that moment in time. The green is the standard deviation for that window. So that's basically how far do my values differ from the average. So as standard deviation goes up, that kind of means like the noisiness of my data goes up, or the variance in my data increases. And then the orange one, the fourth one, this is the result value from that detect function. So this is only going to be a value that's either 0, 1, or -1. So when it's 1, we've detected a positive peak. When it's -1, we've detected a negative peak. And when it's 0, we've detected no peak. So the cool thing is, as I move this board around, let's kind of see how things change. So I'm just kind of slowly tilt it back and forth like this. So you can see the blue value goes up and down as I change it. And that's the raw y-axis acceleration. So you can see it's kind of going up and against gravity. But then notice the red graph is following it also, but a little more smoothly and slowly. And that's because the red value is that filtered average. So think of the red value as the average of the blue value. So the blue value you see has a lot of noise, because as I move this, my finger, like there are little vibrations from my body and things they're changing this, or just noise in the accelerometer. But by filtering out the last 30 values, we kind of smooth all those little peaks out. So you just see what's the overall trend with this. Now the green value, you can see how it's pretty steady. As it goes up again, that just means that there are more kind of jaggies or noisy values relative to that average. So you can see like this, there aren't a lot of jaggy values, and so my standard deviation is pretty steady. But if I shake this thing around, see what's happening there. I've got all these big jaggy values, and the green value shot up. So my standard deviation went way up there, because most my incoming samples are all different. I've got one big sample, and then one small sample, and one big sample, and one small sample. So all of my samples are far away from that mean value. If I just average out all those samples, I get some value in the middle, but each sample individually is very far from that. And so that's what that green value is kind of showing you, is what is that that deviation from the mean. It's kind of neat just to play with this and see kind of how the values change like that. And then notice the orange value isn't really changing, and so that's again the result of the peak detector. So the peak detector is only going to work basically when a blue value comes in that's so far away from the red value that it's actually some multiple of the green value away. It's actually 20 times the green value away from the red line. So when the blue value is far away from the red value by some number that's 20 times the green value at that moment in time, then my orange value will change, because that's a peak. So that's what you see there. So when I flick the board like that, you can see that big spike there. And man, I wish there was a way to stop the plotter here. I'm trying to think. I guess I know a way I could do it. I could unplug the board maybe after I flick it. So let's see what happens. I'm gonna flick the board, and then uh-oh, I did something there. Let's see what happens here. Let's reopen the serial plotter. I might have upset it. Okay, here we go. We'll flick the board, and I will quickly remove it, which might be a bad idea. So flick the board, and then I pull it off. Okay, there we go. So I've probably just horribly upset Arduino. But you can see what happened here, and man, I don't know how to zoom things in, unfortunately, right here with this view. So you might need to bear with me a little bit here, but I'll kind of explain what we see. So here's my red value. Before this impulse happened, the red value is pretty steady, and all of my blue values. So the blue values are the moment in time y-axis accelerometer values. So that's kind of the raw value I'm getting from the accelerometer. The red line is that averaged value, so it's looking at the last 30 samples. So they're both pretty similar, which just means that all of my incoming values are pretty similar to my average, so there's obviously no peak there. But and also notice the green line, that's the standard deviation, is pretty flat. That's just telling me that all of my blue values are really close to my red value. But things change dramatically at this point right here. So this blue value is way up here. Now that doesn't immediately change my red value, but we'll see in a second why. So my blue value is really, really high. My green value is relatively high. It's a little bit higher, but not by much. And you can actually see at the previous moment in time, my green value is really low. But what the algorithm is doing, it's looking at what is the distance from this blue value way up here, this peak, and the red value down here. So at that moment in time, my average was way down here, my peak was way up here. You know, this is a difference of like, this is negative something up to 30. You know, this is a significant difference. And my standard deviation was a really small value, like barely, maybe not even 1, it looks like. So that is a difference where this blue value is more than 30 times larger than this standard deviation compared to this median value here. And so that's when it detects a peak. And you can actually see the orange value spikes up to 1 right here. So orange value goes up to 1. It says, hey, we found a peak. And then you can actually see the next blue value goes all the way down to the bottom, because that's when I flick the board, you know, it pushes one direction and then it kind of comes back, bouncing back here. So it's, you know, you're seeing kind of this vibration back and forth. And so that's when I get a really small value down here. And the peak detector detects that too. It notices, hey, that's a peak in the opposite direction. And so it goes down to a negative value. And I actually get a couple values down there. But that's cool because it's showing me that this is working. And then the other interesting thing is you can see how, you know, that average value, even though I got this giant peak right here, it didn't go skyrocketing way high because that influence value is really small. That influence value is down to 0.1. So it's only taking 10% of this huge peak's value when it's recomputing this average right here. So it just adds a small amount of that peak to it to keep it going. So that's kind of cool. Like, we're visualizing how this peak detector works, and you can see like the standard deviation kind of goes up as these values kind of random, like they fluctuate a lot and change, but then it'll kind of fall back down to a steady state value, and so it's ready to kind of detect those peaks and things again. So this is kind of cool. It's something I recommend kind of playing with and you know, intuitively help you understand how this peak detection algorithm works and why in particular. So if I close this, you know, why it's able to detect the difference between just casually moving the board around like this. You know, if I open up that serial plotter again, I'm getting all those kind of wacky blue values here, but my board doesn't detect a peak yet. It's not until I get a big spike like that that it detects the peak and then starts spinning around like that. So that's what's happening there. Maybe I'll run through some more of the code real quickly to just kind of show what's happening here. But really, all of the magic is in that peak detector.h. That's where we're doing that peak detection. And it's hopefully general enough that you can pull this file out and put it in your own sketch if you're doing something else yourself that you're trying to detect, you know, flicks and peaks and things like that. I should also say the accelerometer on this board has built into it a tap detection that probably has kind of similar logic as this, I would bet, built in. But it doesn't look at a specific axis. Although I do need to dig more into the datasheet to see if there is maybe a way to look at a specific axis. But you know, that's another way that you could do this sketch, and it might be how I end up doing this in CircuitPython. Because the one tricky thing is I need to sample this accelerometer very quickly because I don't want to miss that peak. You know, when I flick it with my finger, it's just like a tenth of a second that it gets that big impulse. And if I'm not sampling fast enough, I might flick it, but if my code wasn't reading the accelerometer at that moment in time, I'll miss that peak, and when it's gone, it's gone. You know, it's like I might catch that tail end vibration of it, but could be in the opposite direction for all I know for that. So I'm not sure, because the problem was with CircuitPython, you're running interpreted code, so you're going to lose, you know, you're not going to be able to sample that accelerometer as quickly in Python code. So I might have to play with a few different options to see if I can sample it fast enough, or if I can't, maybe I can just use the tap detection so that I won't be able to detect the direction. I'll just be able to know, like, did someone touch or tap the board effectively. Okay, so the fidget spinner sketch in the main loop, you know, like I said, I want to prioritize above all else feeding that peak detector as quickly as possible. So I don't have a delay in this main loop at all. So this is the main loop. And in most Arduino sketches, we have like 100 millisecond, 10 millisecond delay. I've got nothing in here because I want this loop to run as fast as possible, just nothing blocking it. Sample that accelerometer as quickly as possible. You know, I haven't measured it, but it's sampling well over 100 times a second from what I kind of saw with some basic testing of this. So that's good because that just means, you know, it's just more chance for me to detect that very quick little flick. So what happens here is I'm just updating, I'm keeping track of how much time has elapsed from the last time that the loop function ran. That drives my animations. We'll see that because whenever you animate movement, I know the velocity, but I need to know the time so I can figure out what's the new position of something. And so that time value is what I'm computing right here. And I compute both the elapsed milliseconds and seconds in floating point because it's useful. I want to specify velocities in like pixels per second, not in like thousandths of a pixel per second or something. So I figured I'd do that here. Here's where I get the accelerometer value and I feed it into the peak detector. So that peak detector.detect, I'm calling the detect function with my accelerometer value. And it's going to come back with 0 or -1. Here's where I turn on that debug output if I'm printing it here. And then here's where I actually look for the peaks. So I want to see if I get a result value that's not equal to 0 because that result is coming from the peak detector, and it's going to give me 0 when it detects a peak. When there's no peak, it's going to give me 0 when it does not detect a peak. So I want to ignore all those cases. When there's no peak, nothing to be done here. If it's non-zero, if it's 1 or -1, then I've detected a peak, but I put in an extra check. So I put in a window of time where after I detect a peak, I will ignore any other peaks that occur during this little window of time. And it's 500 milliseconds that I picked, but you can change it. It's up at the top. It's the peak debounce milliseconds. Because it's kind of like with a button. When you press a button, when you're physically making contact, there's a little period of time where, the metal is starting to touch the metal and it's starting to conduct electrons and starting not to and things like that. And so you get these kind of little fluctuations. And we get the same thing, like when I flick the fidget spinner, I get the vibrations of the board, and so I get that big initial impulse, but then I get, a reverse impulse the other way as it vibrates the other way back. So I just said, you know what, let's just take this little, after I detect a flick, ignore all the other flicks for the next 500 milliseconds, which kind of makes sense because, I can flick it and, a half second later I can flick it again and it'll detect that flick. So that just removes some of that noisiness. The problem would be if I didn't have this debounce, I could flick it and it might catch that initial flick, but then it's also very quickly going to catch the vibration or the reflection back. And so it'll start moving the opposite direction than you expect. Once I detect a peak that happened outside of that debounce window, then I can figure out what is the next window of time for debouncing. And then I just look to see, depending on if you've inverted the axis or not, what's your direction that you're facing. And I tell my fidget spinner class to spin with a velocity that's the same value as the acceleration. And so I'm not getting into all the physics of like trying to model the fidget spinner as a physical thing with mass and inertia and friction. I'll show you. So I made this fidget spinner class under fidgetspinner.h, and this is really all of the logic of the spinning object. So it really just has a concept of a spin function. So when you call spin, you give it an initial velocity. So this is in pixels per second. So this, like 10 pixels per second it might spin around at. And so this is going to be set to the acceleration value, which is coming back in meters per second squared. And this accelerometer, also important to note, I changed the range of the accelerometer in the setup function. So I change it to the 16G range. That's the widest range for this accelerometer. So it's able to detect really large values. But in practice, I'm going to get acceleration values from like -16 to +16. So I know I shouldn't see values that are like 3,000 or something like that, something crazy. So, a value like 16 pixels per second is pretty fast, but I could scale that value if I wanted to change the velocity. But anyways, my fidget spinner, I give it a concept of, I can call this spin function, it's going to start spinning at that velocity. Now the fidget spinner class only keeps track of its position. It doesn't do any of the animation. All of the animation I do in the main sketch. And I did that because I have multiple animation types, and I don't want all of those animations to have to implement all of this fidget spinner logic. So I modeled the fidget spinner as a separate object that just has a concept of what is my current position. And the position is just a value from 0 to 10, which maps directly to the pixel positions. But I make it a floating point value, so it can be like 1.5. The spinner might be halfway between pixel 1 and 2, for example. And that's okay because it's up to however my animation function wants to render that. If it only renders like discrete pixels at a time, it might drop that half and just turn pixel 1 on. Or if I'm rendering a sine wave, I can adjust my phase slightly, and it can more continuously change that value. So, my fidget spinner is basically, it just has a position that spins around values from 0 to 10 based on some initial velocity. Now the slowdown, so you can see like when I flick this and it starts to spin, it eventually slows down, and a real fidget spinner will slow down too because of the friction of the bearing. There's no perfect bearing yet that will spin forever. So it eventually slows down, and I kind of made this, amplify that friction in some ways. Like a real fidget spinner, I think the whole point is to see how fast they spin and how long they spin, whereas this fidget spinner kind of slows down quickly. And I implemented that again. I'm not modeling the physics of this. I started to think about that, but it gets really complex really fast because you need to know the mass of your object, how it's moving, what its normal is relative to the surface, the coefficient of friction between those surfaces, which is really cool. And you could do all that, and you'd probably have to do some numerical integration and things on your Arduino, which may or may not be possible, but you could go that crazy and model this. Or what I did was I just applied exponential decay to the velocity. So I start with an initial velocity, and then just every moment in time that velocity slows down, and it's following an exponential decay. So it will start out really fast, and then it will slow down a lot, and then it'll slow down less and less and less and less and less and less and less until finally it's not moving at all. And the way that you do that is you use the power function. And actually here, I'll show you exponential decay. So if you look up on Wikipedia, this talks about what the exponential decay function is, but you're basically just taking a value, taking the exponent of a small value. So in my code here, in my get position function here, so my fidget spinner, the spin function you call to start the spinning, and then the get position function you call, and you tell it how much time has elapsed since the last time you called get position, and then it will compute the new position, like how far has the spinner moved in that period of time. And so it's just basically going to figure out, okay, it's going to recompute the velocity based on that exponential decay. So it takes the decay constant that you passed in ahead of time, and it takes that to the power of your elapsed time, and then it multiplies your initial velocity by that. So this is just going to scale down your initial velocity over time. So slowly over time, your velocity will get closer and closer to 0. So that's, you can see that as this thing moves around, and as it slows down, that velocity is getting more and more closer to 0, and then finally it gets to 0 and it stops. And then once I have a velocity for this moment in time, I just recompute my position as the velocity times the amount of time that's elapsed, and I just add that to my position. And then I do need to be careful to make sure that my position values fall within the range of 0 to 10, like I mentioned before. If they go beyond 10, I wrap them back around like a modulo operator to, once it goes beyond 10, it goes back to 0. And if it goes negative, I just invert it. So, a -1 value actually turns into a 9 value. Like it starts back around from the opposite direction here. So that's kind of what these two checks do right here. So that's all that the spinner class does. Just given an initial velocity, it will spin in that velocity, and then it will slow down. It will decay at a certain rate. And so that's what happens when I detect the axis. When I detect that flick, I call my spin function and I give it my acceleration value. So it's a little weird that I'm using my acceleration value as my velocity, my initial velocity, but it kind of makes sense because just visually, this thing, like my eye, I'm not going to be able to see this thing moving like 3,000 pixels per second, but I can see it moving 10 pixels per second, 15 pixels per second, 30 pixels per second, and so those are kind of the acceleration values that I get, and so they seem to naturally map well to kind of nice looking acceleration and velocity values like that. So that's what happens there. I call that spin function, which starts the fidget spinner spinning. Then I have a block here where I'm checking my button state. So again, like I said, I want this loop to run as fast as possible. I don't want to have to delay this loop to debounce my buttons. So I'm just like in my peak detector, I have that debounce period where I ignore peaks that happen after a peak. For my button logic, basically I only check my buttons at some fixed interval. So I ignore button changes that happen in between a certain period of time. And so that period of time is defined up here as this button debounce milliseconds. So this basically just means every 20 milliseconds, I'm going to check my button values to see if they've changed, because I want to detect when you release the button. So when I release the button like that, it changes color. And I press it, it doesn't change. I release it, now it changes, and it detects that. It also detects my finger kind of moving the board. And so that's what I'm looking for. I'm looking for a change when the button value goes from high to low, because on Circuit Playground, when you press the button, you get a true value back, a high value, and when you release the button, you get a low value or a false value. We have pull up and pull down resistors on the board that make it work that way. So that's what this button logic does. Basically, just every 20 milliseconds, I grab a new button reading. So that's this little state right here, and then I compare it to my last button reading. So that's what this last button reading was. And basically, if my new button reading is false, which means the button has been released, and if my old button reading was true, which means the button was pressed, so I'm looking for that transition from pressed to not pressed, then I ratchet through and change, for example, button 1, I increment my animation, and I modulo it by 4 because I only have 4 animations. And then for the color, if you press the other button, I increment my color, and I modulo it by the number of colors that are in that big color array thing at the top that you saw before there. So that's all the button logic. And so the nice thing is, a lot of cases when you're looking at buttons, you might read the button, delay for 20 milliseconds, read the button again. But that doesn't work here because I don't want to just spin time in a loop, wasting time with that delay. That's going to slow down my whole main loop. I want my main loop to just keep running and running and running and feeding that peak detector with samples as fast as it can. And then every 20 milliseconds, the main loop will say, oh, it's time to check the button state. And then, it's going to go again and again and again. And then it's going to check 20 milliseconds later. Okay, what's my button state now? And has it changed? And it can detect those changes and change the color or the types of animations and things like that. Okay, and then the last little bit here is I'm telling the fidget spinner to get the current position. So just based on the amount of time that has elapsed since the last time this loop ran, compute your new position. And we just looked at that a moment ago. It's using velocity. It applies an exponential decay to the velocity so that it slows down to kind of simulate friction. And then it recomputes the position based on that decaying velocity. And then I just look at what is my current animation. So I keep tracking a variable, just a value 0 to 3. There are 4 animations. And just based on the current animation, I call a function. So I have an animate dots function and an animate sine function. So this is the animate sine function. They take in parameters. You can pass in the frequency of the sine wave. So with a frequency of 1, you get a value that looks like that. And with this, you get a value that looks like this. This is the frequency of 2 in this mode. And so this is kind of nice in that if I flick it, you see there are kind of 2 humps to it. Or if I change the colors, you can see more easily there's like a red and a green. So it's going between the primary and the secondary colors like that. So that's kind of cool. It's just changing the animations. I'm running a little bit out of time, so I'm not going to go through the animation functions. You can look at these down at the bottom. I've done this in a lot of videos. I'm just using a sine wave or a dot. I'm just computing based on the position of my fidget spinner. So these are all passed in the position. And remember, that position is a value that goes from 0 to 10 exclusive. So it's going to go from 0 to like 9.99999, but it's never going to actually be 10. So based on that value, my animation function figures out where should I draw the dot. Based on the position of that fidget spinner, it might be at position 0, it might be position 1, it might be position 1.257844321 or whatever, and it has to figure out how to draw the dot accordingly. Or maybe if there are 2 dots, it can figure out how to draw those dots around the board. And you can actually have 3 dots. I'll show you here. Maybe we'll change this so that the second mode adds like 3 dots. The unfortunate thing is if the number of dots is not a multiple of, or is not, if 10 is not evenly divisible by the number of dots, you'll get some kind of weird behavior. So, okay, you can see in this mode, I've got 3 dots now. Hey, this is triple the fun. And so I can click that and I can flick it and it'll spin around. But see how it kind of gets into this weird state where they don't, really move the way you might expect. That's just because there's only 10 pixels. If I have 3 dots, those don't evenly divide into that, so it's going to be a little funky. I can change the sine wave though. That thing is a little more even. So let's say 3 peaks instead of 2 peaks for the 4th animation mode. So we'll load this on the board and see what this looks like in a second here. So this will probably be a little more sparkly kind of interesting animation. Okay, so we'll go to 1, 2, 3. Okay, so this is 3 peaks. So when I click that, you can kind of see that's kind of neat. Let's see, let's change the color a little bit so that, let's do blue and red, kind of pinkish color. That's kind of cool. So you see there are like 3 red dots and then a nice little smooth gradient in between those that goes around the board like that. So that's kind of cool. I kind of like that. You know, the sine wave with multiples that, or with values that aren't evenly divisible into 10, that seems to work, but the dot values, maybe not so much. But you can add, you can change these values, you can tweak these as much as you want inside of here. So, okay, I think that's it. I'm going to wrap this up. It's been an hour, so I don't want to, I usually try not to go too much longer than that. Like I said, this is the digital fidget spinner project. This works with both Circuit Playground Classic and Circuit Playground Express. So this is the Express board that I have right here. And it's kind of cool. You know, you have a little fidget spinner with no moving parts. There's no bearing to wear out. There's a battery to die now, unfortunately. So this is perhaps the only fidget spinner with no moving parts, but the only battery-powered fidget spinner that I'm aware of also. So hey, there's some trade-offs here, but it's kind of cool. You know, this is just demonstrating some of the neat things that you can do with the accelerometer on Circuit Playground. You know, the accelerometer detects force, so it's useful for detecting things like gravity, but it can also detect a very big force, like me flicking something or, you know, touching something or really shocking that system. But the tricky thing is, how do you detect a strong force, you know, a strong instantaneous force like that, while ignoring this slower kind of motion, you know, that just, you know, this less intense but constant force. And so as we saw in this video, I walked through this peak detection algorithm that uses the average of a window of samples and the standard deviation to figure out when a new sample comes in, if it's far enough away from that average, based on some number of standard deviations, we've detected a peak. And so then, you know, we can start spinning the fidget spinner around like that. So really cool project. You know, hope folks check it out. If you have a Circuit Playground, you can play with this. Again, it works with both the Express and the classic version of Circuit Playground board, so you can load up the fidget spinner and go to town with it. And you know, if you make some neat variations of this, then be sure to show them on the Show and Tell every Wednesday at 7:30 Eastern on Adafruit's YouTube channel. You know, join that hangout and you can show off your own version of the fidget spinner, because that's the cool thing with fidget spinners. You know, I don't know, I'd love someone, I'm sure someone's writing a book on fidget spinners right now. There's going to be a coffee table in the next 5 years at least that chronicles the fad of fidget spinners, because I'm old enough to remember things like snap bracelets and all of these things. You know, so that 20 years from now we're going to go back and remember, oh, you remember that fidget spinner thing? Huh, whatever happened to those things? But I wonder, what is the alpha fidget spinner? You know, what was the very first fidget spinner? And then the fun of it is that everyone has kind of taken it and made their own fidget spinners. So this is my variation of it, my digital fidget spinner using Adafruit Circuit Playground board. So if folks have questions, throw them into the chat and I'll see if I can get to them real quick. Oops, let me move to the main view again. So there's that. And let's see, let me turn on this fidget spinner. I like the brighter one is a little bit nicer for this one, so this is my favorite one. And let's see, let's change it back to that sine wave mode, and let's do kind of the blue and turquoise colors. So that's kind of cool. Oh, that's kind of cool. I got like a slow kind of spin there. This is kind of the fun of it, is just playing with it intuitively to understand kind of, you know, does it feel like a real thing? That's kind of the art and science of coding something, and when you make something that feels organic, because you can see the code that goes into this is very much not organic. You know, it's computing statistics and things, but that turns into something that feels like a living kind of thing, or a physical thing, which is kind of cool. So I like projects that explore that kind of crossover of areas. Okay, let's see. So some of the questions here. And let's see, is this C++? Yep, this is C++. This is Arduino, the Arduino programming language. It's based on C and C++. Like I mentioned, in this video, I'm doing this project with Arduino. For the next week's video, I'm hoping to try and redo this project on Circuit Playground Express, but using Python, CircuitPython. So we'll see if I can create a digital fidget spinner with Python. Like I said, it's going to be tricky. I'm not sure I can sample it fast enough, so I might have to make some compromises. I mean, worst case, there are buttons on the board. If you press the button, that could start the fidget spinner potentially, so that's one option for it. Let's see. I'm trying to activate a capacitive screen without my fingers or hands nearby. Is there a way to do that? For a capacitive screen without your fingers or hands, not that I know of. Like, you could probably get like a stylus, you know, the little styluses you can buy like at a dollar store that you use for your phone. And the tip of that has a little conductive tip, and so that is probably something you could use if you had that on like a robot arm or something and you wanted to touch with. But anything conductive should, in theory, set off a capacitive touch screen. You just need to be careful. Like, you probably don't want to go rubbing aluminum foil all over your the front of your nice camera or your phone screen. Okay, let's see. And where can I learn more about working with Circuit Playground Express and other boards? Great question. So I will link to the product page for both Circuit Playground and Circuit Playground Express. So these are the two boards. This is where you can purchase them. But if you check out on here, there is a link to the tutorial. So this is for Circuit Playground Classic. This goes into all kinds of details about how to use this board and how to set up the Arduino IDE to program it. And then if you go back to the product page down at the bottom, this will link to a bunch of other Learn System guides. So if you want some other cool ideas of what you can do with Circuit Playground, check out all of these projects here. So there's lots of cool stuff, like, hey, make a wrist version of this or something like that. That'd be kind of fun. And same thing for Circuit Playground Express. And like I said, Express is the brand new version of Circuit Playground. Just came out last week. It's out of stock right now, but hopefully pretty soon it'll be in stock. So you won't see as much. There's just a few guides for it right now. So this stuff is coming a little bit later compared to the classic board. So, you know, if you're not as familiar, if you're totally new to Arduino and things, you might want to start with the classic board that has more guides and things available for it. So cool. I think that's it question-wise. So I will wrap up this stream. So thanks a lot for watching. So this is Tony from Adafruit with the digital fidget spinner project. So I made a fidget spinner with no moving parts that uses Adafruit's Circuit Playground board, the all-in-one electronics learning board. Check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos. Check out twitch.tv/Adafruit. That's where I stream these things live. I like to stream at least every Friday. Last 2 Fridays, I was at PyCon, the Python programming language convention. So no streams last few weeks, but we're getting back into the swing of things, and you'll stay tuned for lots of CircuitPython and MicroPython content. So like I said, next week I'm hoping to do the fidget spinner, but using Circuit Playground Express and CircuitPython. So tune in for the thrilling conclusion to the digital fidget spinner project. But until then, we will spin all of our fidgets like that. So thanks a lot for watching. I'll see you guys later. Oh, and click the like, the comment, the subscribe button. Let us know that this is cool content, and we'll keep making stuff like this. So until next time, this is Tony from Adafruit. Thanks for watching. See you later.